So we'll just very quickly we'll do a recap of the stuff that we were talking about, right? With the discussions that we had done, and then what we'll do is we will take it up from the point where we had left it off in the last class. So over here, so let's just very quickly have a recap of the content that we had been talking about. So first of all, so basically we started talking about the Basel models, and within the Basel models, what we were doing was, so within the Basel models, we started talking about the PD model, right? So we discussed the overview of the Basel model framework, and from there we moved on to talk about the PD model, where we saw the different approaches of developing the PD model, right? And in such a case, what we were doing is, so after that, so when we started talking about the model development approach, so we talked about a few important model development approaches, like we talked about the linear regression model, we talked about the logistic regression model, we talked about the survival analysis model, and for IFRS 9 PD models, we talked about the lifetime PD models, we talked about the time series approaches for incorporating the macroeconomic variables and so on. So we had a discussion on each of these portions. Right? Now, having said that, the next, so in order to develop these models, in order to go to the have an understanding of the statistical implications of these models, we needed to have an understanding about the sampling distribution, right? We needed to understand how an estimation is to be done, what or how is it that a particular testing is to be done, and so on, right? So we had explored, we had talked about all these specific models in place. Now comes the next part. Now we need to have an understanding of the models. So in today's discussion onwards, I will start talking about the models that we had talked about. So we have talked about the overview of the descriptive measures. We talked about the statistical inferential measures. In the last class, we saw how a sampling distribution can be created. Also, what we all saw was that so how is it that the sampling distribution can be created? How is it that an estimator can be constructed out of it? And how is it that the properties of the estimator, like unbiasedness, can be checked? We also looked into it that whether that element, how is it that the significance of that estimator can be studied? So this is what we had seen in the last class in our discussion with SAS. So we had seen it on the SAS platform. Now we'll be talking about this. So now from today, today we'll talk about the broad models of or the broad statistical models of developing the PD model. Now, when I'm talking about developing the PD model, along with this model, I'll also talk about the modeling approaches which are used for developing the LGD and the EAD model as well. So when I'm talking about the modeling framework, when I'm talking about the modeling algorithm, I'll talk about all the three kind of models that are in place, right? So, so basically what we will be doing over here is we will try to develop, we try to understand the modeling frameworks, right? So we'll talk about logistic regression, we'll talk about decision trees, we'll talk about random forests, we'll talk about time series, survival models, and so on. So we'll explore end to end of the algorithms for or the framework of these models. And when we do that, we will try to understand, we'll try to link it back to the type of models that can be developed, right? So even though I'm starting my discussion with respect to PD model, right? But as I progress, I will be bringing in other modeling approaches as well, the other basic modeling approaches, and we'll talk about how is it that this model can be, or to explain which type of behavior what model can be used, right? So that is what we will be discussing in our today's session. Guys, give me just a minute and we'll get started. right? Okay. So what we'll be talking about over here in today's session, we will be focusing on the modeling part today onwards. We'll talk about modeling approaches like linear regression, right? We'll start with linear regression and we'll go one by one. We'll see how it can be implemented in SAS and where is it that linear regression can be implemented. To develop what kind of model can I implement? Linear regression. How does linear regression work? What are the basic nuances of linear regression? So we will be talking about the modeling frameworks, right? So but before we start off with anything, so we talk about a lot of model development and model validation and everything. So the first question that comes out to us in our minds is that what exactly is a model? So if I talk about a model, right? So the question that comes out of here is what is a model? Okay. So when I start talking about a model, so the first question that comes out to me in my mind is that what exactly is a model? Or in terms of a risk model, I like to understand what exactly is a risk model. Right now, basically talking about a model is nothing but it's a replica or a representation of a situation or of anything. So it's a replica. Now, when I'm developing a credit risk model, it's a replica, right? Now, when I talk about a credit risk models, what am I trying to replicate? What am I trying to frame an understanding about? So, in a credit risk model, or say in any predictive models, what we try to assess are the key factors which drives the riskiness in the model. If I talk about a credit risk model, so in a credit risk model, the question that comes out is that what is it that we are trying to model, or what? So in a credit risk model, what we are essentially trying to do is we are trying to capture elements of the riskiness. We are trying to identify those factors which affect or which impact the riskiness of a particular borrower, right? So in a credit risk models, our objective is to find out the key risk drivers. The key risk drivers, right? So the question that comes out again over here is so basically the question that comes out over here is that how do I identify the key risk drivers? So when I am trying to assess the key risk drivers, right, a very important question of causality comes in. So which are the factors which causes a borrower to default? which would help, what are the factors which would cause the loss or which would cause the recovery to happen, what are the factors which would cause the account to default, and what are the factors that we can use to identify the exposure value. So every time whenever we are trying to develop a model, we are trying to develop a relationship between the dependent and the independent variable. So when I talk about key risk drivers, so there is always an element of causality. So there is always an element of causality. So this causality is always between the dependent and the independent variable. And the modeling approach that I would take for my model development would be dependent on the independent and the dependent variables. So this is where the role of causality comes into play, right? So basically what I'm trying to do is whenever I'm trying to develop a model, what I'm trying to do is I'm trying to assess the factors or assess the causality relationship between the independent variable and the dependent variable, right? And when I'm trying to assess the causality, so the role of the models is to help us assess or accurately assess the causality between the dependent variable and the independent variables, right? So that is something which becomes very important for us as well. So so if I look into this, so there is an element of causality into this. So there is the dependent variable, and there are a set of independent variables, right? Now with this particular thing, the next question that comes out to us is the following: that 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 what are the type of dependent variables, and for each of the dependent kind of variables, or for each dependent variable, how is it that you would choose your models, right? So basically when I talk about causality, right, so there are, so causality is between two things, the dependent and the independent variable. And when I talk about the dependent variables, so there is one set of variable, it's a categorical dependent variable. Single dependent variable. Okay. So the next part is, so there are these two types of variables. One is the categorical dependent variable, the other is the continuous dependent variable. And the independent variables can be a mix of continuous and categorical variables, right? Now when I talk about categorical dependent variable, so if I want to model the categorical dependent variable, then what I have to use is, now if it's a categorical dependent variable, then the model that we would use is the logistic regression model. Okay, over here what I'll have is I have the logistic regression. And when I have my dependent variable as a continuous variable, I will have a linear regression. It's the linear regression. So basically, whenever you have a dependent variable, you have a categorical dependent variable, right? What you can use is the logistic regression. And whenever you are trying to predict a continuous dependent variable, what you use is the linear regression. Now, before we move to talk about linear regression, logistic regression, and anything, can you tell me what exactly is regression? So basically, we have all heard these terms, right? So what is so regression, model development, and linear work. So what exactly is regression? What does regression mean? So can you just put your answers on the chat box? Okay. So I have the following answers for regression. Regression explores the relationship between independent and dependent variables, helps analyze the relationship between variables, techniques to establish relationships, based on a set of observations, predicting the values on set of independent variables, the equation to find relationship between dependent and independent variables. Fine. Now, let's say that okay, so relationship is between independent and dependent variables. Fine. Now, instead of regression, if I use correlation, right? The correlation between two variables. So I see that x increases, y increases. So I say that fine, x and y are positively related. So as your x increases, y will also increase. So based on x and y, I can take an inference. I can make an inference. Right? Or let's say I have a I have a moving average, and based on that moving average, I take my predictions. So What then is the most important feature of a regression model? So how is then a regression model different from all these other measures that I have talked about?
So, Sushil, this side,
Yes, sir.
as regression tells us the unit increase in the independent variable, how does the dependent variable will increase, right?
Right.
But correlation only tells the level of relationship between the independent variables. For example, X age and salary is the two independent variables,
Hmm.
and 0.7 is the correlation. It is telling about that there is a high relationship between them, but it is not telling about if I increase 1 unit of increase in age, what will be my salary, right?
Okay.
So this is the main difference between regression and correlation.
Okay. Fine. So the next thing that I would ask you is that when you are developing a regression model, you end up with an error, right? Now, if regression is predicting the value of the dependent variable correctly, why are we then getting that error? Because the
Because the
definition that you have
correlation is less.
said is correct but incomplete, right? So there is a very critical aspect which is missing in this definition that all of you have given.
It is
Yeah.
the best fit line, Sarma.
What is the best fitting?
Like the correlation, it kind of establishes relationship,
No,
right? So
correlation. So
whether the
correlation,
variables
what
are
Sushi,
proportional or not
yeah. So what
proportional.
Sushi said about correlation regression, that's absolutely perfect. So, but then,
Yeah.
what
So
what is this best fit line? What is this best fit line?
so we have
Best fit
variable.
line is
One
that
by one, one by one, one by one. Yeah, please carry. Yeah, who was speaking? Please carry. I missed out your name.
So, Tanmay, regression explore the linear relationship between the variables. Uh,
Now, my
and I
question
think
as
is,
someone was saying, it was the best fit line. Best fit line represents that line that represents the whole population. Means all the points are there into the space, and that equation that represents the points spread on a
yeah. So
space. That
what
we are
is
saying
it
is that
that
this is the
yeah? So what is it that regression predicts? What is it that regression is predicting? That is my question. So all of you have put down the definition of
and
linear regression, but there is something critical which is missing. So what is that
Tanmay,
best
I
fit
think
line? Sorry?
so for the best fit line, I think the correlation between dependent and independent is maximum, and the partial dependency between the independent
Oh,
variables is minimum,
oh.
and then the stability of the relationship is also maximum. So there are some
No,
two
you
or three measures of a
cannot
best
estimate
fit
the
line.
stability of a relationship from this best fit line. So all you can say is that that line, whatever I have constructed, is the best representation of the population. So that's the best reflection. So so what is it that regression is giving you? What is it what does regression mean? Regression is not the fact that there is an independent variable, there is a set of independent variables and a dependent variable. No, that's not regression. Regression means something else. The term regression itself means approximating to mediocrity. So, what regression gives you is not the actual value of the variable, it gives you the expected value of the variable. And because it gives you the expected value of the dependent variable, that is why you always have a error between the observed values and the predicted values. So basically, when you are defining regression, right, so this is a question which many interviewers come out with, that what is regression? And regression is not linear regression. Regression is a class of models. Now, when the relationship between x and y is linear, then we call it a linear regression. If the relationship between x and y is non-linear, it's a non-linear regression. So regression itself is a class of model which helps you to estimate the mediocre value of the dependent variable, or it approximates the value of y to mediocrity. Now, what do I mean by this term mediocrity? What it means is that given a average behavior of the variables in the past, based on its average behavior, or based on the most representative behavior of the data in the past, basis that you are trying to predict what possibly could be the most average behavior that this variable can show. And that is why there is always an error, because the observed outcome or the actual outcome that you generally see is not a part of only the average behavior. It is a part of the average behavior plus a random plus a certain uncertainty which we call the randomness, right? The random term in the error in the regression model that we can see. So when you are defining regression, regression is nothing but the so it's a methodology which is used to assess the overall or the average behavior of the y, or try to predict the average behavior of the y basis a average prevalent behavior of y in the past, right? Now, any deviation from that value is not predicted, because that happens as an element of randomness. Because randomness cannot be predicted, so the only thing that you have is the expected or the average behavior of y. And that is entirely the idea of any predictive modeling. So you have a given behavior, right? You have a given historical behavior, and then what you are trying to do is you are trying to predict the dependent you trying to predict a value for the dependent variable, a forward looking value of the dependent variable. So that is the very reason, that, when you are developing the model, we are uh, what should I say? So we are so cautious about the population stability, because if the nature of the population changes, then the model is not going to predict, because it has been based on a given average behavior. Because if the population averages change in the future time, right, that's where your model will not be performing. And why is it so? Because you are trying to predict the average behavior of the dependent variable basis the average prevalent behavior of the variable in the past. And how are you predicting them? You are trying to identify the most important factors which would explain the movement of the dependent variable, right? So that is the reason why the behavior of the variable should also not be changing very much. That is where we look into the characteristic stability index. So when we are trying to assess all kind of population stability and character stability and everything, what we essentially try to do is we try to ensure that there are no major changes in the overall average behavior of the population from that time point based on which the model has been developed and the time point when the model is being implemented. Because if that changes, then the entire model would also be facing issues in its performance, right? So summing it up, so all of you had stated the correct thing, stating that regression is a methodology to predict the dependent variable basis a set of independent variable. But the answer was incomplete in the sense that you are not predicting the value of the dependent variable. You are trying to predict the average value or the expected value of the dependent variable given a set of independent variables, right? Because when the vector of the independent variables would change, the dependent variable value would also change. So the expected value of y that you are seeing over there is nothing but it's a conditional expectation. You are trying to find out the expected value of y given a set of independent variables. So the entire objective behind regression is to find out the expected value, the future expected value of the dependent variable basis its average behavior in the past, right? And it is this very, it is this very term expected which makes the very difference from a conceptual perspective, right? So ensure that the fact that you convey to the interviewer the fact that the dependent variable that you are predicting is an average value of the dependent variable. It is not the exact value. To make it as close as possible to the exact value of the variable, what you need to do is you need to minimize the errors. And to minimize the errors, there are multiple algorithms which are used, and it is these algorithms which create the different kind of, or the different classes of the regression models that we generally see in our day-to-day work. Right? So is this part clear? Yeah.
Tanmay, when we say this is the best line, so the best fit line is the random component minimum, or how we define a
So
line as a
I'll
best fit
come to the best fit line later. I'll come to it when we move over with linear with regression and the framework. I'll come to that. Right?
line? Okay, okay.
Okay. So the next question that comes out is, so basically the most fundamental model of any regression algorithm is the linear regression, right? And this is perhaps the most simplest classification algorithm which we talk about, right? So any machine learning models would start off with a linear regression classification algorithm, but this particular algorithm is highly underplayed in the day-to-day life. I mean, in the modern, so we often do not consider the sophistication that this particular model has. Now, this particular model is very simple, and the very implication of being simple is that it gives you results very quickly. And hence we are not often fascinated by this, but the algorithms which go into making this linear regression model is extremely interesting to and it's very fundamental to understanding the basics of any classification algorithm. Now, even if you are thinking about machine learning algorithms, linear regression and logistic regression are the two basic classification algorithms, right? Then comes decision trees, random forest, blah blah blah, and so on. So we'll first start off with our understanding of linear regression, and we'll explore all the components of linear regression as well, the challenges that are associated with linear regression. We'll talk about autocorrelation, we'll talk about heteroscedasticity, we'll talk about issues like model misspecification, we'll talk about variable transformation, and we'll talk a lot about each of these statistical methods, right? We'll talk about outliers in a linear regression framework and so on. So we'll talk about each of these. So the first thing that we need to talk about over here. So let's start off by talking about linear regression. Now, if I am to explain the concept of linear regression to someone who doesn't understand linear regression, who is not statistically oriented, what do I mean by the linear in a linear regression? What is this linear? What does linear mean? Linear regression. And over here, what does? Yes. What does linear?
Directly proportionate relationship between independent and dependent.
Correct. This is absolutely correct. So linear relationship means that they are proportionately related to each other, right? And that is why you can actually use a straight line to approximate the relationship between two variables. So this is why we write it as y equals to a plus x. Correct. Absolutely correct. Now, now, when I am doing a linear regression, then what am I trying to exactly do? What I am trying to answer over here is that does a straight line does a straight line approximate the relationship between x and y? The relationship between x and y. So saying that given the readings on two variables, can I say that, or can I safely say that x and y are proportionately related to each other, right? And that this is where when I need to address this, so my objective is to reach a best fit line and show that the linear relationship is the best possible fit, and that whatever could not be explained in the relationship, or by the or whatever differences lies between the predicted and the actual points, is actually a random error. So it's because of certain randomness which has happened. It's because it's not possible for us to capture it in the model. So this is where the concept of the best fit regression line comes in. So the objective of developing any regression model is to reach the best fit regression line. The best fit regression line. Now, how does this best fit regression line work? So let's say I have a diagram like this. So I have my x series over here. I have my y over here. So now let's say I have the scatter plot between x and y looking something like this. Right. So this is something that so this is a given scatter plot. Right? Now what I'll do is I say that okay, I put a regression line through this. Now observe that this black line that I have drawn over here can be treated as the best fit regression line. Why? Because this line can approximate the observed behavior very closely, right? What it means is that the type of scatter plot that this graph had, the straight line, by putting a straight line I can more or less approximate that relationship that was described in the scatter plot, and hence because I can approximate it through the straight line, I can clearly say that yes, this line is the best fit regression line because that gives me the highest capture rate. So this becomes my best fit line. Now let's say I have another plot. And I have this y over here. Now let's say there is a plot which looks something like this. Okay. Now let's say I put a straight line over here. Now can I call this black line, now this straight line, the best fit line? Now most probably no. The reason being that this straight line cannot actually approximate the relationship, the observed relationship between x and y. So what it means is that this relationship between x and y is not linear. So therefore, when I'm trying to develop a linear regression, what I'm trying to do is I'm trying to assess whether this model or whether a linear relationship fits between two variables, right? And the best fit line will show me. Now first of all I check that whether a relationship, linear relationship or a proportionate relationship between x and y holds or not. Now okay, fine, it holds. Then what are the matrices or how good is that fit? So when you are trying to say that okay, this is what it is, this is what the fit is and this is what the fit is not, that is where you need to define that. So this is where, that is where you are defining your goodness of the fit, right? And when you are talking about goodness of the fit, what you are trying to say is that how good is it that as the equation, given equation can approximate the observed relationship of the observed relationship which is displayed by the observed values of x and y, right? For the second case over here you will see that this is the part which at all cannot be captured by the line. So it is going up, and that is why x and y is non-linear. So a linear relationship between x and y or a proportionate relationship between x and y cannot capture the last part of the distribution. Hence, a linear fit will not be appropriate, and you will see all your measures of fit are very low in this case. Your variances in the estimates will be very high. So that is precisely what this is precisely why we do linear regression. So linear regression is not something which is done out of an absolute decision. So you apply this model, you develop a model on this on the data to see whether linear relationship holding or not, whether relationship can kind of bring in that element of proportionality or not, right? And then you keep on trying out other models and then see which is the one which best captures that actual plot, right? So this is what is linear regression and your best fit line. Now, after this, the next or the most basic part which we need to understand are the assumptions of the linear regression model. This again is a very important question which comes out in many credit risk interviews, right? They ask you directly that what are the assumptions of a linear regression model? Yes, so those of you know what the assumptions are. Can you just come up with the answers over the chat box? Okay, so the first assumption that I get is heteroscedasticity. Okay, so should there be heteroscedasticity or should there be no heteroscedasticity? So which is the one which so no multicollinearity, no autocorrelation. There should be heteroscedasticity. So ideally there should be no heteroscedasticity. There should be homoscedasticity. Okay. Relationship between dependent and independent variable. Okay, fine. So what is the most basic assumption of linear regression? The most basic assumption. Okay. So the first and the most basic assumption between of a linear regression model is that the dependent variable should be a continuous variable. Right? So the first and the foremost assumption is that a linear okay, let me put this down. So Akhilesh says normal distribution. So normal distribution of what? Okay, so let's look into the assumptions one by one. Assumptions of a linear regression model. Number one, so the first and the most important assumption is the independent variable and the dependent variable must belong to real numbers and be plottable on a graph. So this is a very fundamental assumption. It's a trivial assumption, but it's an important assumption, because if any one of them have imaginary values, then you cannot develop a linear regression model on them. So the independent variable and the dependent variable both must have a continuous must belong to the set of real numbers, right? Mhm. Variables and the dependent variables must belong to the set of real numbers plottable on a graph. So if they are not real numbers, then you cannot develop a model on them. So they have to belong to x belongs to r and y belongs to r. The second assumption that comes out over here, it's a basic assumption, is that the independent variable, sorry, the dependent variable has to be continuous in nature, and while the independent variables can be a mix of continuous and categorical values. Okay. So the third is the independent variables must be non-stochastic. The independent variables must be non-stochastic in nature, while the dependent variables can have a distribution attached to it. Right? Okay. Now comes the next part. The independent variable must be non-stochastic in nature, and the model. Okay. Number 4. The model has to be linear in parameter. Has to be linear in parameter, but not necessarily. But not necessarily in variables. So the model has to be linear in parameters, but not necessarily in variables. Number 1, the error term is assumed to be white noise. Now, which implies homoscedasticity, no autocorrelation, and a mean which is equal to 0. So this is what the most important, these are the most important assumptions. Now the question that comes out over here is, so the variables can be made variables can be linearized by appropriate. Okay. And finally, the most so another last but not the least, the dependent variable is to be normally distributed. Though I would not put this as an assumption because this can be derived from the fact that the error term is a white noise. So the next part is there must be no association between the independent variables. Right? So these are the 6 assumptions, the 6 most important assumptions of a linear regression model. So the first and the most important assumption is that they must be real numbers and maybe plottable on the graph. That's absolutely important, because if they are not real numbers, then what you will end up with is a the challenge of plotting the imaginary numbers or the complex numbers, which is not really a part of it. So which is outside the scope, because we are dealing with real data sets, and hence that the assumptions or the data point must be plottable on a line. Now the second question that comes out is the dependent variable has to be continuous in nature. So whenever you are trying to model a dependent variable model with continuous dependent variable, that is where you use linear regression. Let's say, for example, for LGD model development, if you're trying to predict the recovery, for the other model development, which is for the EAD model development, where your exposure is a function of certain factors, but exposure itself is a continuous value. So for different cases, for different situations where the dependent variable is continuous in nature, so that is where your linear regression is used, and hence LGD and EAD would be the two places where we would be talking a lot about linear regression. But at the same time, not for all continuous variable can you use it. There has to be other criteria as well. And what are the criteria? The criteria is that, so the second assumption is the the third assumption is the independent variables must be non-stochastic in nature. So what it means is that this x value there should be provided values, there should be true values, and there should not be any probabilistic behavior associated with these variables. Right? So xi has to be non-stochastic, because when I'm predicting, right, when I'm trying to predict the yi, I have the yi hat of the estimated value plus the error term ui, right? So that yi has a distribution attached to it, ui has a distribution attached to it. So the x's that I am using to predict the ui, if they also have a distribution attached to it, would mean that the prediction that we are doing is absolutely random. So basically what I'm trying to say is that when you're building the model, right, the data available with you is or the variable should be non-stochastic. Now the question that comes out over here is that how do you make a variable non-stochastic? So I'll just come to it in the next slide. Now the second part is the relationship with the model must be linear in terms of parameters. So it should be alpha plus beta x. It should not be alpha plus beta square x. Because if a model becomes non-linear in terms of parameters, right, then that model always remain parameters non-linear, cannot be linearized. Now the next question that comes out over here is the model has to be linearly variable in parameter, but not necessarily in the variables. Now, if the variables are non-linear, then you can use certain transformations, lower the ranks on plots, and you just get your transformed variables. But that is not the case for the for the previous assumption. Now the next part is the model has to be linear in parameter, but not necessarily in variables. Done. Now the next part is that when I'm trying to develop the model, when I'm trying to create the structure of the model, right, the error term becomes very important. Now this error term is a white noise error term. So it is what it means is that the error value that we are getting to see over here are not predicted, or they are not kind of values, but so they are not predicted values, but so they are not deterministic values, but they are absolutely random values, right? And this randomness is there to talk about, to capture those factors which we cannot capture through our models, right? Let's say, for example, there are two people who work for 10 hours each throughout the year, everything else remaining unchanged. There is one guy who gets a rating of 8 on 10, and there is another guy who gets a rating of 8.2 on 10. Now that may be because of certain other factors, because of the fact that the manager prefers one guy compared to other, because of some reason that is outside the control of this guy. That's the random factors, right? So so the model, so the error term, this random term, so these errors must be random in nature. There should not be any deterministic pattern to them. Because these areas, this is random, right? So how do I know whether it's random? If it's white noise, so if the error terms are identically independently distributed, I'll say that yes, they are white noise. And what are the characteristics of white noise? The characteristics are the mean is zero, the variance is constant, so that there is no homoscedasticity, and there is no heteroscedasticity, and there is no autocorrelation between the error term. So the error term of two time points will be absolutely uncorrelated. So the covariance between the errors of the first data point and the second data point should be absolutely uncorrelated. So you take any two errors and you just try to find out a correlation, you will get to see that no, there is no correlation. So not having any correlation across the error terms, between two error terms, is known as autocorrelation. So basically, if your error term does not have any autocorrelation, so that it means that et and et minus 1 are two independent error points, right? So they evolve independently of one another. If the mean is 0, means all positives and negatives cancel out. The variance is constant, it means plus 5, then it goes to minus 5, plus 2, minus 2, so that's random. So exactly the amplitude on both sides of 0 is the same or is similar, right? And the variance is constant. So it ensures these three characteristics together ensure that the line that we have constructed is a random line. So the errors which satisfy this, the locus of this line, will be a random error, because there would be no possible pattern to the error. So it should not be increasing, monotonically increasing or monotonically decreasing over a period of time. Because if that's the case, it means that the model that I have now is not an optimal model. So I will only be having an optimal linear regression model if the estimates that I have obtained are the best estimates and the error term is 0. So what it would imply is that this is the most optimal model, because whatever I could have interpreted or whatever variation I would have captured, I've already captured. Whatever I've not captured are white noise or random terms. Now, after this, the final and the most, so another important characteristic is no multicollinearity. Means that whatever variables enter into the model should be independent of each other. They should be in a position to explain the dependent variable on their own, and hence we assume, we take it that there should be no multicollinearity across the data, so across the independent variables, right? So this is the next point. So these are the assumptions of a linear regression model. So any questions up to this point?
Tamay, can you explain homoscedasticity again? I missed that.
So homoscedasticity means constant variance of the error term. Let's
Okay,
say,
okay.
let's say
I got it.
you are in a learning by doing process, right? So over time your error will go down, and that means what? The error is predictable, right? So it's not a white noise. But so your variance is going down continuously and it's gradually increasing or not decreasing. Now your variance is constant. So every time it can plus 5 to minus 5, then as well plus 5, as well minus 5, plus 5, minus 5, like this. So it means the constant, so the interval is going to be plus minus 5, right? So that's a constant variance. The variance is always constant. And the variance is constant. A constant variance would imply that the particles are moving out in a random manner. So they can move plus, but it's, whatever is happening within a limit. So minus 5 plus 5. So it can be anywhere between minus 5 and plus 5. So that is what, that is where this thing comes up, right? So homoscedasticity and zero error together ensures, and autocorrelation together ensures that your error term is a white noise. That it's whatever could not be explained was not possible for explanation because they were random components.
Correct. Okay. And what is non-stochastic?
So non-stochastic means that it does not have any probability distribution associated with it. So if x is 5 means x is 5. So it does not have a distribution. I'll not say it is 5 with this probability and 10 with some other probability. It's not like that. It's not stochastic. There is no probability distribution associated with the x's. The x's are non-stochastic. They are numbers. Like the data that you see. Right? So that why do you do the data quality check? To ensure that all the figures in the place are fine. So there is no movement in the behavior of the variables, right? So that is why you do that. So non-stochastic means that your x, the value of x that you are seeing, is a certain value of x. There is no uncertainty in it,
Okay. Yeah. Thank.
right?
Yeah. Thank you.
Okay. Now, assumptions of linear regression is a very important question which is asked in interviews. So if you do 10 interviews, 7 interviews would be there which will ask you this question. Especially if you are applying for an opening which involves stress testing, CCAR kind of a job. Because over there, linear regression is used extensively. Or if you are into kind of a marketing analytics kind of a job, or so within banks you have this marketing profiles, right? Or you are in a model or in a regulatory profile where LGD models are being developed. That's where linear regression will become very important in that interview, right? Okay. Now comes the next part. Now the next part is about specification of the linear regression model. Okay, and one more thing. Okay, no. Tomorrow session also we'll have it from 3. That's fine. Okay. So the next part, which becomes very important for a linear regression model, is your model specification. How do you specify the model? Right. So let's try to understand that. To specify the linear regression model, there are two components. One is the population regression function. The second is the sample regression function. So there are these two measures. So the first that I have over here is the population regression function. So I'll have population regression function. So I'll have the population regression function. Now what is this population regression function? So the population regression function is defined as yi guys, just give me a minute. I'll just be back and we'll get continued. So as I was saying, population regression function. So yi is equal to alpha plus xi plus ui, where ui follows normal distribution, it means 0 and sigma square u. So this is the first and the most important specification, and we call it the PRF. Now because this is the population for us, this is not known to us, and this is something we have already discussed at length, right? That the population is not is unknown to us, and hence alpha and beta is also unknown to us. So alpha and beta are the parameters, are called the parameters of the regression equation. So what does this say? It tells us that yi, the dependent variable yi, is composed of alpha plus beta xi. So it is a function of the xi, and it is also a function of a random component ui. Ui, which follows a normal distribution with mean 0 and a variance sigma square u. So it means that this ui that I have over here is normally distributed. So this variable is normally distributed with a mean 0 and a variance sigma square u. So there is an element of randomness involved in this, right? So this is something that we have already seen. So, so the yi, or the observed or the realized outcome, is an outcome of two things. Number one, the alpha plus beta xi plus the random term. So one part is the random term. So this ui is your white noise or your random components. But there are always certain movements, certain uncertainties which keeps on creating fluctuation in the behavior. So this is the random factors. Now the question that next comes out over here is that what is this alpha plus beta is? How do I interpret this? Right? So now let's start looking into, let's try to understand this. Right? Let's say I have a data on exposure on one side and utilization on the other. there is EAD. So what is EAD? EAD for us is nothing but the exposure at default, right? Now, given this EAD, there is an element of so there is also this utilization. So what we are trying to do is we have taken utilization as a very important variable, and we want to know that okay, how is it that EAD and utilization work and so on, because I need, if I can gauge the relationship with the coefficients, then I can put that, I can feed that in to get some other outcomes. So over here, EAD is the first thing that I get to see. And over here, what I also have is utilization, right? Now, let's say I have utilizations like 0.85, 0.85, and let's say I have 0.90 over here. Okay. Now for this utilization, let's say my exposure at default is 2000. Okay. Let's say the exposure is 3500. Okay. So now what I have done over here is corresponding to some set of utilizations, I have written down the values, right? The exposure. Now observe these two values. Now over here your utilization is 0.85. Over here also your utilization is 0.85. But the two values over here are two different values. Right? So your exposure is your dependent variable and your utilization becomes your independent variable. So higher the utilization, my conjecture is higher the exposure at default. So what happens over here? So now how do I try to address this? So one thing I can see is that there is always an element of probability associated with utilization as well. So given that utilization is zero point 0.5, what is the probability that it is 2000? So it's not always 2000, right? So as your values change, now if you look into this utilization variable that I have written, right? So there are different values of utilization. So if I think about it, that there is a box from where I'm drawing out the utilization values between 0 and 1, then this utilization is a random variable, right? So the distribution gets attached to this utilization variable. Now the utilization variable itself is an independent variable. So now if I try to predict this relationship between utilization variable and EAD, EAD has its distribution, utilization also has its distribution. So I'm predicting one stochastic variable basis the other. Makes no sense. So in order to predict EAD, I need to have x's which are not stochastic. So what do I do? What I do is I very technically shift the distribution on the dependent variable, right? So now what I say is that fine, if this is the case, then I will look into the distribution that EAD will have given the utilization is 0.85. So given that utilization is 0.85, I look into the distribution of the EAD values. So this is 2000, this is 2500. Similarly for 0.9, I will again get values like that. So it is 3500, 3000, and so on. Right? So now what you can see is that given this value x, given a value of the dependent variable x, there is a distribution of the y values. So the y finally that I will calculate out over here, so the y that I will calculate out over here will be nothing but it would be the expected value of y or expected value of EAD given x is equal to 0.85. So this becomes the expected value of EAD given x equals to 0.85. Now here I am saying that, here what I say is that I assume that the relationship between EAD and utilization is proportional. So as utilization increases, everything else remaining unchanged, the exposure at default will increase proportionately. So over here what I say is that this expected value of y given x is your alpha plus beta xi. So this alpha plus beta xi is nothing but the expected value of y. So this is your average behavior, or as we call it, your deterministic behavior. So the observed outcome or the population, the observed outcome is a function of two parts. One is your deterministic or your average behavior, and the other is your random factors. Because there is a random element, you see that every time utilization is 0.85, EAD is not always 2000. EAD varies, so there are some other differences as well, right? So the yi that I get to see, or the observed, the actual outcome yi that I see, is a function of two things: alpha plus beta xi plus ui. So it is yi is equal to alpha plus beta xi plus ui. So that is, it is comprised of the deterministic component plus the random factor. And it is this deterministic component that we can predict. We cannot predict the random factor. So our optimization algorithms would be targeted to minimize the impact of UI on our estimates. Right? Is this part clear? Any questions up to this point? Any questions up to this point, guys? Is this clear? Go through this. Okay. Okay, fine. So over here, but this alpha and beta in the population regression function is not known to us. So alpha and beta is unknown. And that is why we need to predict them. Unknown. So what, so how is it that we can kind of predict them? So to predict them, what we need is, so as we have already seen, that that based on the sample that we have with us, we can predict, our objective would be to predict the population parameter, right? So over here what I have is the sample regression function. We have, what we have over here is the sample regression function. So what is this sample regression function all about? So the sample regression function about here is okay. So the sample regression, so the question that comes out over here is how would the sample regression function look like? The sample regression function looks like something like this. Yi is equal to alpha hat plus beta hat xi plus I, where ei follows a normal distribution with mean 0 and sigma square. So this is your sample regression function. So our objective over here is to use this alpha hat and beta hat to predict alpha and beta. So over here, yi hat is alpha hat plus beta hat xi plus ei. The ei follows a normal distribution with mean 0 and sigma square e. So you have these two parts. Now the question that comes out over here is that how do we go about predicting? So based on the sample regression function, our objective is to predict the dependent variable yi. So the regression equation finally looks something like this, that yi, or the observed value of yi, is nothing but it's a sum of the predicted value yi hat and the error component I. So it is the sum of these two things which give us the observed value. Right? Okay. So our objective would be to minimize this error component. So this is the part which has to be minimized. This is the part which has to be minimized, right? So how do I define this error? So this error over here will be nothing but I is nothing but the difference between yi and yi hat. Is the difference between yi and yi hat. So this, so our objective now is to minimize the error. The question that again comes out over here is, how is the error minimized? So how is the error minimized? So over here, and in most of the econometric algorithms, right, it is the error, it is not the error which is minimized, but it is the sum square of the error which is minimized. So over here, what our objective will be to minimize the sum square error. The sum square. So this is the SSE. Right? So the algorithm which we use to minimize the sum squares of error is called the ordinary least square algorithm. So the OLS, so the linear regression model is, or the algorithm which minimizes the sum squares of error in in the linear regression model is called the ordinary least square estimation. The ordinary least square algorithm, or as we call it, the OLS algorithm. Right? The OLS algorithm is used to minimize the sum squares of error and obtain the best fit value of alpha hat and beta hat. So this is something which we would be doing in tomorrow's session, right? So we'll start off with the OLS tomorrow. We'll look into the OLS equation. We'll look into the properties of alpha hat and beta hat. We'll see how they're estimated, what are their distributions, how is it that what are their sampling distributions, what are the key characteristics, and how is it that the derivation of alpha hat and beta hat is obtained from each of the assumptions, right? So this is, so tomorrow we'll do a dissection of the OLS algorithm, its key properties, the estimators, and their sampling distributions. right? So thank you guys. Uh, thank you for your time, and let's catch up tomorrow.